So I will talk about gravitational waves in digital. So as we know, historically there was much confusion about the nature of gravitational waves, and famously the Bondi-Sachs formalism clarified a lot of this confusion. And in the Bondi-Sachs formalism, there are a few quantities which play very important roles. I will write the names because these are the quantities we are after in digital case. So we need some analog of the Bondi-News tensor. Then we need some analogs of energy and angular momentum. And flux formulas for energy and angular momentum, and a concept of asymptotic symmetries in this interest. So in the Bondi-Sachs framework, these are super translations. And all these quantities play a very important role in modern applications of gravitational waves, astrophysics. Like all these things play an important role in gravitational wave astrophysics. So if we try to generalize this theory to lambda positive, we encounter unforeseen difficulties. So lambda positive, there are unforeseen conceptual difficulties.
Just yes. So the problem, I suppose, was that there was no clean notion of localized stress energy tensor in gravity.
Yeah.
That's why you have to measure everything at infinity.
Everything at infinity. And then you come up with very good set of variables, which will capture the nature of gravitons and will give you a good notion of mass and momentum.
But that something is happening in the spacetime, you can see just from curvatures, right?
Yeah.
But it's just measure the energy.
Measure the yeah. Okay, so when we try to do this for positive cosmological constant, there are unforeseen conceptual difficulties, and the subject is still not settled. Yeah, please.
One confusing thing is that there isn't even a time lag in gravity.
I will discuss one of this. Yeah. But so there are many conceptual difficulties, and as Poincare is suggesting, we don't know where to start. But in the last 8 years, there is a lot of development. And the purpose of my talk is to give an overview of this development. So let me start with some history of this subject. Strominger gave us Dirichlet boundary conditions in de Sitter. These boundary conditions are analytic continuation of ADS boundary conditions. These boundary conditions, everything is very well understood. There is no confusion. But these boundary conditions are not interesting for study of gravitational waves. Because in these boundary conditions, what happens is that null rays bounce back, which essentially means that there are no gravitational waves in this setup. So although they are fully under control, they are not interesting.
Can I also just say one thing which you know very well, sorry, which is that they're not even physical, because you know, if you look at some scalar field and you look at how it evolves, you compute the wave function, so to say, as a function of various boundary conditions the system has, right? So to insist that it's Dirichlet.
Yeah. Also, from cosmological point of view, you would like to attach de Sitter to something else, and there you would like gravitational waves to propagate further. So,
and just along those lines, if you attach it to an inflationary universe, I mean the perturbations we see today, so to say, don't correspond to Dirichlet at all, right? So this is just nothing.
But they're part of the trick in computing the wave function, right?
They're part of the trick. But the trick is that, Shiraz, you impose some non-trivial boundary. You say that the fields take some non-trivial boundary values, and then you compute.
Not zero, yes.
Not zero. You know, that's like too restrictive.
Okay, so the other extreme of this is also proposed by Strominger. This is no boundary condition. Okay, and there are many variations of this. So, so completely I plus free.
This proposal was in this DSCFT paper?
Yeah, this is in the DSCFT context.
And where was this proposal?
This is original DSCFT.
Yeah.
And this is a little bit later, around 2010.
Okay, all this, the Chern-Simons theories, these non-unitary, that time?
Well, Strominger wrote purely gravity papers on this and also those papers.
Yes.
So, it was in those papers. So in this, you impose no boundary conditions, I plus is completely free. Okay, so it's fair to say that this is not fully understood. It's certainly not useful for the gravitational waves related work because as Onkar pointed out, there is no good notion of time-like Killing vector. There is no universal structure at the boundary. So we cannot define a good notion of mass. We cannot define good notion of angular momentum. Certainly there is no progress with regard to gravitational wave theory with these boundary conditions.
What is this boundary conditions? Boundary condition should be in some space, at some spatial boundary, or what?
Well, global de Sitter doesn't have spatial boundary. It only has time-like boundary. Yeah. And you would like to impose boundary conditions in the time-like direction. You want to say what is the sense? You want to come up with a notion of asymptotically de Sitter spacetimes, so asymptotically in time.
Yeah, but I mean, I agree with the spirit of Abhijit's question because, in a sense, okay, the natural thing, is that you specify the state in some manner, and it determines what the final values are. So for example, if you take the no boundary Hartle-Hawking state, then it has some amplitude to take various boundary conditions in the far future. That's the natural setup. I mean, that's the spirit in which one computes the wave function as a functional boundary conditions. Right?
So when you say certain boundary conditions, somehow you are exploring a subspace of states. Perhaps
I would guess so. Yeah.
I mean, one dimension or very small.
Yeah, I don't know how to answer that question in a proper way.
We should go ahead.
So Strominger et al. Have come up with this idea that one should not impose any boundary conditions at I plus, but these boundary conditions are difficult to work with in settings where you want to make sense of gravitational waves and de Sitter is because there is no universal structure at I plus.
Can I ask something? And I'm really sorry if I'm preempting things you obviously develop, but there is a nice Brown-York stress lens.
There is a Brown-York stress. I will say a lot about it later. Yes. Yeah. Okay, so since there is no universal structure, like it's difficult to talk about energy momentum cycles. Okay. And just to make one comment about this discussion, actually there are people who have tried putting boundary conditions not at the full boundary, but only at one point. So, like people have considered space-like slices of this type, and they have tried to put boundary conditions only in R. But this is like sort of the spatial infinity. It won't help to understand the gravitational waves. So I will not discuss these.
But I mean, when you say these boundary conditions here, there is also something
in the past. Yeah, I mean, there are people who have discussed both things together, future and past, but I will only concentrate on the future part of this talk.
So what mechanically can I think of this is computing some transitionality where your state is fixed by boundary condition.
Perhaps you can take that way. Okay, so from this discussion it's clear that we should come up with some middle ground.
So the recent boundary conditions of Victor and Chandrasekhar are they going to play any role, like where you introduce?
Those ones I do not know. I mean, my talk is purely in the gravitational setup. Yeah, those ones I do not know, but something similar has been explored actually. Yeah. Okay, so from this discussion, yes.
This might be a stupid question, but the vertical lines are Scri plus Scri minus, the null-like infinity in this Penrose diagram.
The vertical, yeah. So the vertical, I mean, these horizontal lines are the boundaries of de Sitter. These are Scri plus.
Okay.
Suppose you just looked at, let's say, scalar field in de Sitter, and looked at all its solutions.
All the solutions, yeah.
And then you look to see what happens at infinity.
Yeah.
Is there a certain rigidity of, is there a sense in which the space-time looks more or less similar for all of these, or does it change very much?
Actually, I will discuss this point.
Okay.
Yeah, this is the main point actually. Yeah. So as from this discussion, it's clear that we have to choose some middle ground. And what is the middle ground? That is the main question. So there are three setups in which people have worked with such a middle ground. So one is linearized gravity. In Poincare coordinate. Other is linearized gravity in Bondi coordinates. And third is a nonlinear theory in Bondi coordinate. Okay, and for this talk, for string theorists, I think it's easiest to describe the nonlinear in Bondi coordinates, and that's what I will discuss mostly in this talk. There is workable framework for all these three things, and these are the main references. So it's fair to say that the subject in the modern form was started by Ashtikar, Bonga, and Keshavan. In 2015, they wrote 5 or 6 papers on this subject. Then after this, Iskenderis et al. Pointed out that not only in Poincare coordinate, but also in Bondi coordinates, one should analyze this physics. And this paper, compared Ferrucci and Luzziconi, did a lot of technical analysis in this subject. These authors, these are relativists, Crucial, Jahanurhat, and Spolka. They studied linearized gravity in Bondi coordinates and clarified many important things. And very recently, there is a paper by Bonga, Bunster, and Perez just 2 weeks ago or so, which makes, in my opinion, good progress. Subject, but as I said earlier, the subject is still not settled. We don't know. We don't have answers to all questions. Okay, so with this, let me start. Okay, so in flat space, what happens is that as we go to infinity, GAB becomes eta AB, and there are 1 over R terms. In this is something that does not happen. So if you take a metric GAB and which you would like to call naturally asymptotically de Sitter and subtract the de Sitter metric, this will be of order 1. For the same reason, because if the gravitational waves are traveling, then they will change the boundary metric at infinity, and because of this, the difference will be of order 1, not fall off with 1 over R.
It may be order 1, but it freezes after a point, right? Time evolution stops. If you've got some more of a certain wavelength, and you wait long enough, it stops oscillating. That wavelength just keeps going.
Oh, you mean after the cosmological horizon? Is that what you're talking
about? Yeah, you just wait long enough.
Yeah.
Almost all dynamic stops, right? So you say that it changes from de Sitter, but then for over a certain time, and then stops, right? Is that right?
Okay, one can say that.
In co-moving, just to put it in co-moving
coordinates,
once you exceed once the wavelength goes out of the horizon,
yes.
So if you've got any finite wavelength excitation, it can only have a finite effect on your space because it only acts for a finite amount of time. Is that right?
Yeah. One can phrase it in those terms.
What he's saying is you just compare the final metric with the fiduciary.
Yeah.
And there is some small change, presumably.
Yeah, but the change is not small in the 1 over R sense. because the gravitational waves will come and hit the boundaries, they will change the boundary metric.
Yeah,
so that is what one is.
It's out of one, but what I was saying is it doesn't build up with time. You wait for an infinite amount of time, it doesn't go to infinity. It just freezes.
Yeah. I mean, finite change.
Finite, right.
So you're doing beyond linearized.
Beyond linear. Yeah, I mean, well, actually, even in linear theory, this part remains the same.
Yeah.
Okay, so let us try to make this precise. What does this mean? So I will make this precise in a setup which I think many of the people here will be familiar. So I will do this in the Poincare coordinates to begin with, because that is
I was going to say, when you said constraint here is Bondi, yes.
No, I will discuss Bondi in a moment. So we just look at GAB, which is A squared G0 plus epsilon H, where G0 is minus beta squared plus B X squared. Now what we can do is that we can study the linearized equations of motion.
This coordinate system covers what part of it?
Oh, the Poincare part. Poincare part will cover only this part. Okay, so now what I will do is that I will look at linearized equations of motion for H, and I will analyze this in Fourier space because that is the simplest. This is just to bring out a very important point which I want to talk about. So this is like this. I K dot X. Actually, this is something. If you have done a course in cosmology, or if you have not a course in cosmology, you must have done this. So now what we are looking at is the equations of motion for this H and HK eta S. S is the spin. S is not important. And what we find when we do this analysis is that HK, I mean, there are two, it will give rise to a second order differential equation. Maybe I will write this equation. The equation is something like this: HK double prime minus 2 over eta H prime plus K square H.
The boundary is eta equals 0.
Yeah, boundary is at eta equal to 0. This line is eta equal to minus 8. This line is eta equal to minus 8. Okay, so when we solve this equation, we find normalizable and non-normalizable solution. So the decaying solution goes as eta square, and growing solution goes as HD is order 1H. 1. And in fact, it's not difficult to write down the exact modes. So the exact modes are theta sine k theta minus 1 over k sine k theta. This is the one that goes as theta square near eta equal to 0, and the other one is theta sine k theta plus 1 over k cosine k. Okay, this is the one that goes as 1. There.
And the freezing is simply the statement that near eta equals 0, the k squared h is small compared to the.
Yeah, near eta equal to 0, that statement is there.
Yeah.
Near eta equal to 0, this is the term that dominates. Yeah.
So just like
that. Because then what happens to the mode doesn't depend on how it's varying. It's point by point. It's independent of k. The behavior in eta near the boundary is independent of how you're varying in space, just like in alias.
Just like
Alias. Right? That's why you get local renormalization.
it's a fiction.
Yeah.
In omega is independent.
That the behavior and radius is independent of what you're doing in the section.
Is omega independent?
Omega, if you want to
It's a
consider.
damp toss. Actually, prime is time, so it's
Yeah.
actually an oscillator with friction. The middle term is first derivative. It's a friction term which wins out, right? So it just brings the system to this.
Yeah. Okay, so you see now we have a mode expansion in the Fourier basis, what we can do is that we can compute the symplectic 2 form for these linearized solutions for decision.
I have a question.
Yes, please.
So when eta goes to 0, doesn't the friction term diverge? I mean, I don't get.
No, it diverges, but still the solutions are of this type.
I mean, if the friction term diverges, then I guess.
So one can solve the equations anyway.
Yeah, velocity also goes to 0, acceleration.
Yeah. It's less and less.
Maybe one way to think of it is that you have a differential equation, you solve the differential equation and take the limits, how it behaves with the.
No, in the limit eta goes to 0, the other terms just simply drop out. I mean, you just have 2 by eta each prime equals 0 or something, right?
No, the derivative terms will not drop out. You have to keep track of the derivatives. It's like in a differential equation. If the derivative is fast, then you have to keep track of the derivatives.
Okay.
Okay, so let us call the coefficients of these modes to be the standard notation for electric modes, and the coefficients of these modes to be B's. Then what we can do is that we can compute the symplectic 2 form. So if H and H bar are 2 perturbations, then roughly, I will not write the exact expression. The symplectic 2 form goes like this. E bar B star minus E B bar. I can put the star in one place. The stars we don't remember. Okay, but the key point is that it goes as the product of electric modes and magnetic modes. That's the key point.
Position and momentum.
Position and momentum. Yeah. So now if you put Dirichlet boundary conditions, which is setting the growing modes to 0, all the B's to 0, if you put B's to 0, then there is no dynamics because omega is 0. Or if you put only magnetic modes, that is only growing modes, and E is to 0, then again dynamics is 0. And this is simply the fact that you have discrete space, and if you are freezing the metric here, then using time emulation you can come on such a slice, and on such a slice omega is again 0. So, I mean, because you have freezed the boundary metric here, so omega is 0. Using conservation d omega equal to 0, we come on such a slice, and here also omega is 0. So there is no dynamics. So in order to allow dynamics, you have to allow both electric and magnetic modes. In this sense.
Amitabh, maybe you explained that why is there a reason you are calling this electric and magnetic?
Yeah, there is a reason. Corresponding to these linearized perturbations, you can compute the electric and magnetic part of the Wild tensors. And electric part of the Wild tensor will have this as coefficient, and magnetic part of the Wild tensor will have this as. That's it.
Roughly, B is like the induced metric, and E is like the normal error.
Yeah, yeah. B is the induced metric, and E is the normalizable perturbation.
Normal error. G dot.
Yes. Yeah.
So at the boundary, does EK vanish or something? I mean, because eta goes to 0, then the sin k eta also goes to 0, I suppose.
Yeah.
So,
yeah, this goes as eta square.
The EK, not the BK. The BK.
EK. Yeah, so this goes as eta, and this goes as eta, so the eta term cancels. As a result, it goes as eta square. And here the cosine term dominates.
Okay.
And
Yes.
again, to go back to this point that sort of more natural to think of initial conditions and as dictating a state. If you think about the Hartle-Hawking state, there are no boundary state.
No boundary state.
Even in Poincare coordinates, that amounts to a certain boundary condition. So if we put that boundary condition, it relates the two modes to each other.
It relates the two.
So then that's one sensible way to find a middle group, so to say.
Exactly. So this was the first setup that Ashtekar, Bonga, and Keshavan started. They analyzed the linearized gravity with linearized distributed gravity in Poincare patch with zero boundary conditions at the Poincare.
I see. Is it zero or is it?
The metric perturbation is zero, right?
Okay, that's actually not, I think, what comes out of this observation. I think it's purely in
so the boundary condition is that no radiation coming from
nothing going. Yeah, I think it's nothing going in.
No radiation.
Yeah, that's the correct one. But that's the one they have.
That's the one.
Okay. Yeah, that's the one that comes out.
Yeah. Okay. Okay, so now we all agree and we understand in what sense we have to allow both electric and magnetic. So now we will do this in Fefferman-Graham form, and I mean I will start by doing it in Bondi form and then translate it into Fefferman-Graham form, which we will all understand. Okay, so this is the Bondi-Sachs.
Even though you were using Poincare coordinates, you could have been analyzing global areas.
I could have done this in global areas. The same will come out. Yeah. Actually, there are many variations of writing this formula. Some people write it as delta G wedge T. So delta G is the variation of the metric at the boundary. G0 perhaps is the better notation. And TAB is the boundary stress tensor. Ashtekar et al. They write it as delta G wedge TAB, which is the electric part of the wild tensor, which contains the same information.
Not putting any boundary condition at the horizon.
At the Poincare horizon, if you insist on analyzing things in Poincare areas, then we will put the boundary conditions that at theta going to minus infinity, the radiative part of the field goes to zero. Yeah, because that's the only case the green function is well studied.
Yeah, that's the Bunch-Davis.
Bunch-Davis.
Sorry, to pick my point again, I mean, this EK thing, I mean, if EK goes as eta squared, then at the boundary we go to zero, right? I mean, if you say that eta is zero at the boundary, then EK goes to zero.
The A is 1 over h eta. The A is 1 over h eta.
Right.
So if you multiply with A square eta square, so this one is 1. But A square eta square times 1 is 1 over eta square. So you see, one mode is finite at the boundary, one mode is 1 over eta square at the boundary. I mean, actually, boundary is not the correct word in these coordinates, but you see the behavior.
1 by eta square then diverges.
The metric also diverges. You have to go to T. I mean, you can analyze this in other coordinates. Like, I mean,
it's very much like ADS. Yeah. Where the metric diverges at the boundary, normalizable modes are less divergent.
Yeah.
It's just like
that. Yeah.
Okay.
I think you can go ahead. Yeah.
Okay. Okay, so best way to explain this is perhaps give a comparison between flat space and digital. That will be the simplest way to get the point across, and at the same time, I will be able to relate to the Fefferman-Graham discussion. So I will write some equations for lambda 0 and for lambda positive. So for lambda 0, we have future null infinity, where we are doing this at the null infinity. But here we have future time like infinity. Okay, we will work with a setup. In asymptotically flat space time, this is R times S2, and here we will work with a setup where the boundary metric is also
sorry,
R
but
times
just ask
S2.
you one question. Fine, is GR7. They say it's time like infinity, but it's a space like slice. I mean, what is the reason to call it time?
Okay.
I am forever confused.
Oh, because we call it's
Sorry,
sorry.
sorry.
If no,
No. I mean, I'm sure.
future space like infinity.
No. I mean,
No, I
right.
no, I said it wrong. I said it wrong.
Okay.
Yeah.
No, but there's something anti-constant null infinity. Because null rays reach there. I mean, I don't know.
Yeah, some people call it null infinity
Yeah.
because null rays reach there. Yeah.
Okay, all right.
Yeah.
Okay, fine. It's fine. Sorry.
Yeah.
Okay,
The
sorry.
name is a bit funny here.
Yeah, sorry.
Okay, but in the diagram, you know what we are doing. Okay, so in this case, the main discussion that has occupied people in the last many years is the fact that there is a geometrical description of all this. People keep on insisting that asymptotically flat space times at null infinity must admit conformal completion, geometrical description, and things like those. I don't know how relevant all that is, but the same discussion can be applied here. But modern developments are all in the coordinates setup, and here also almost all the modern developments are in the coordinate setups. Okay, so the coordinates that people work with.
So sorry, why is this R cross S2 not S3?
It's conformal to S3. If you add 1 point,
Yeah.
then it becomes S3. But the setup that is simplest to analyze is R times S2. I mean, if you put a point particle in decitor and that point particle reaches the boundary, then naturally from S3 1 point is removed. So that's it. Okay. So the so let me write the only one and complicated metric. So this is Bondi matrix. Okay, so we want to analyze our difficult asymptotically notion of asymptotically discrete spacetime in this setup. Okay, so let me say. So this metric has almost all things general. So V is a function of R U X A. Beta is a function of R U X A. These U's are functions of R U X A. GAD is a function of R. Everything is very general. There are 4 gauge conditions that have been used. The conditions are GRR equal to 0, GRA equal to 0, and determinant of this is fixed. So GRR is 0, GRA is 0, and this determinant condition. So in that sense, if you can impose these conditions everywhere in your spacing, then this will be gauge fixed. But of course, we will not really, I mean, we will analyze this in powers of 1 over R. So these are the gauge conditions. Okay, so now when we analyze this in flat space, what comes out or what is natural?
You're going to say this, but in a minute, I'm sure. But yeah. Just to understand you will analyze the asymptotics, right? Yeah. But I mean, just to connect it to something as R goes to infinity, beta also blows up, or
no. Beta will.
Okay.
Yeah. So the diagram is like this. So these are constant U lines.
Okay.
And R is taking along these lines. So R goes to infinity when we reach the boundary. But on these lines, R is changing. Yes. Okay. So in flat space, what happens is that UA goes to 0, beta goes to 0, and V over R goes to -1 plus 2m over R. Okay, and gamma AD goes to gamma AD plus CAD.
So when you say this happens, is this a condition you impose, or the equations of motion force this?
No, so you in flat space-time, you have to come up with the right set of boundary conditions and analyze the equations of motion too.
But you could have done something different.
Yeah, people, I mean, in the last 10 years, everybody is doing something different. This is the original Bondi-Sachs analysis.
Yes, it's flat space.
This is flat. So this is lambda equal to 0. I'm writing this for lambda equal to 0 now.
Okay. And these coordinates you're describing are in De Sitter, right?
They cover they both. So they are valid for both.
Just the choice of gauge.
Yeah, this is just choice of grade. And I can analyze my Einstein's equations order by order for lambda 0 or for lambda positive in this case. Yeah.
So these boundary conditions are setting one of your E's that equals to 0.
No, I will come to that discussion is for De Sitter. I will come to that part. Yeah,
this is like
this is
one of the most.
No. So this actually there is no such thing in flat space. The boundary metric. If you put these things here, then there is boundary metric is just null metric. Like
That's kind of what I have in mind. Like you're fixing the metric.
The boundary metric gets fixed. And mass M is the a function which carries information about the mass, and CAB is the most important function in this discussion. This is called the shear, and
Amitabh, a question that is you can choose not to take it. You're probably going on. But could you have like in ADS we could have imposed ADS boundary conditions? Or changed the metric and imposed those ones. Could you have done something like that in flat space and got something sensible? Or are you forced to? Yeah.
So many people have tried, even people from TF or postdocs have tried this. Chandramoli and other people have written papers. In my opinion, one does not get much mileage out of it.
Nothing interesting happens. So this is the only reasonable space-time in that space.
Because you want to ask various other questions, whether these boundary conditions are compatible with your space-like infinity boundary condition, whether they are compatible with your time-like infinity boundary condition, whether the asymptotic symmetries can be matched across all these places. So such questions.
Perhaps I can clarify. I was hoping to get a space that solved Einstein's equations with lambda equals 0, but was not flat space. I'm not trying to get a better definition of flat space. I'm trying to generalize beyond flat space. Is there an interesting way of doing that? Do you happen to know?
No, I don't. I don't know the answer to that question. But if you demand if you demand that the at infinity you get future null infinity, then I don't think there is much choice.
I'll just say one last thing and I'll shut up. You see, in ADS, we could have had ADS space, but there are these interesting asymptotically locally areas.
Yes, they will come here in De Sitter.
Okay. I've never seen an analog of that in flat space, and I was wondering whether such things exist.
So space-like infinity is where my PhD work lies. And in space-like infinity, there is no such choice. You cannot change, you don't have freedom. At null infinity, I also think there is not much freedom, but I don't know.
Space-like infinity.
No, space. So like if you analyze Einstein's equations near space-like infinity here.
That's space-like.
Yeah.
So
and just specifically, is there some one-time reason why there's no freedom? It's like
the nature of equations are very different. I mean, although we just add one small term to multiple constant, but the equations.
We'll ask the question.
No, I was asking if Shiraz would be asked even Euclidean space. Whether there is a notion of some
Yeah, what was the question?
I'll ask by analogy. So in ABS, we can impose ABS boundary conditions and we get ABS. But we can also impose asymptotically locally ABS boundary conditions, which corresponds to changing the field theory by turning on by sources, right? Yeah. Okay. So I was wondering whether in flat space there's the analog of the normalizable modes, which are S matrices, right? Set waves.
Yeah.
But what are the analogs of the non-normals?
That's what it is. So there are these things called asymptotically locally equivalent spaces, right?
Okay.
So presumably you can analytically continue.
Sounds interesting.
It's an interesting topology.
They are not flat, right? They have some curvature. Is that asymptotic? Okay, anyway.
But R mu alpha becoming.
Full thing.
Yeah.
It satisfies sense equation lambda.
Because gamma AB was the flat sphere. I mean, this
round metric on the sphere. Yeah, round metric on the sphere. Yeah. Okay, so the determinate condition forces CAB to be traceless, and CAB traceless means that it has only two arbitrary functions, and those two functions are the polarization of the graviton. And generic modes should be allowed in flat space, so CAB is essentially arbitrary. Once you have such things, one can write down the formulas for the energy, which is simply the integral of m over the sphere, and one can write down the formula for the energy loss, and this is essentially NAB. NAB. This is called the Bondi news, where NAB is partial derivative of u derivative of c. So I mean, this works wonderfully in flat space, and since this is, I mean, positive quantity, one has various positivity property of Bondi energy. Okay, so we want to do the same thing for digital, and we start analyzing these equations, and what we find is that beta is not fixed. So when we do this analysis, we find that beta is a function of urxa, which was this function. This just becomes beta 0 urxa plus order 1 over r. Okay, so the digital equations do not fix beta.
Is this analogous to saying that the non-normalizable
modes are allowed? Yeah, or like saying that local deformations of the boundary metric are allowed.
So, sorry, Amitabh, can I ask a question?
Yes, please.
Even in the flat space, beta is fixed to be 0 only to the leading order, right? There is still 1 over r corrections in flat space to beta, right?
Of course, there are 1 over r corrections, but here there are.
Here, even the leading one you're saying is not fixed. There is some.
Yeah.
Okay. And same is the case with UA. There is 1 over r on the left side, but okay.
That's the same is the case with the U.
Sorry, I'm already said it in this. What is the consideration that tells you that this freedom is allowed here and not there?
Oh, Einstein, just analyze Einstein's, expand each of these V, beta, U, G, everything in powers of 1 over R, and analyze Einstein's equations order by order, and see what are the constraints you are getting.
No other consideration.
Nothing
about
asymptotics. Nothing. I mean, asymptotics is all contained in this discussion. Like we have a metric which is sufficiently complicated, and we analyze Einstein's equations order by order in powers of R.
Hi. Can I just have a comment here?
Yeah.
Yeah, I mean, the thing is that the initial data is only GAB. So you just prescribe GAB, and the other component of the field, the follow-up of the other component of the field are given by Einstein equation. So the initial data you give in Bondi-Sachs only GAB. So only the angular part of follow-up you give, then all the beta, UA, all this quantity you will get from the Einstein equation.
I will come to that. Yeah, Janu. Thank you. That's a second order comment. I will come to that. Yeah, so Janu is my collaborator. He's making a technical comment about something I'm a little bit wrong.
I'm sorry. I'm just saying that you're expanding around R going to infinity.
Yeah,
is physically saying that you're expanding around a very big sphere.
R in my case, R times S2. R times S2. And I mean, I'm just doing this. So, actually, so instead of drawing constant U lines, if I draw constant R lines, then these lines are different. And then I am analyzing equations, like exactly what Fefferman-Graham expansion does.
Right. But I was trying to, since you're not saying you're working in perturbation around AD, is it?
Yeah, there is no perturbation.
I'm trying to understand what it means that you're saying R goes to infinity in some geometrical sense. And is that one of the things I see is that your compact space is becoming very large.
Yeah.
And something else is also happening at the time.
No. So this is related to some Fefferman-Graham discussion.
I understand at the level of equations.
Yeah.
I was just wondering what. I'm sorry, I'm not even sure the question.
I also had a similar question, which is, I understand, I'm sorry to be so dumb, but I understand Fefferman-Graham in terms of coordinates, your coordinate system, the natural thing would be to start with Poincare, right?
No. So I'm now doing Bondi. I don't even know which part of the de Sitter it covers actually. I'm doing Bondi. So
locally you can write
locally, I mean,
something like that.
I think what it does is that it covers region of this type in de Sitter. Yeah. Okay. So I have to write 2 more equations. Sorry, this is a bit technical. So beta, only the leading part. I mean, is not fixed. Similarly, U is not fixed. V, the equation of motion tells us that V over R going to lambda over 3 e power 2 beta 0 times R squared plus something. And QAB is arbitrary. Or rather, if you say gamma AB is arbitrary. Okay, so you see, not much has come out of the equation of motion analysis.
What was gamma?
Gamma is the GAB is the expansion of powers of R. So gamma AB is arbitrary, beta 0 is arbitrary, U is arbitrary. Just some equations require that V should be fixed in this way. And what this means is that if you look at the metric.
Amitabh, hi, can I ask?
Yeah,
hi. So even in flat space, I think this may be related to earlier Shira's question. If I allow gamma to be smooth sphere metric and allow it to vary, then the beta will be, I mean, the spacetime will still remain asymptotically flat because Weil tensor will go to 0, but beta will be order 1 even in the, I mean, there will be order 1 term in beta even in the flat case. If your gamma is not a unit sphere metric.
Yeah. Yes.
It's like turning the sources. Right?
Yeah, I think beta is order 1, but UA goes to 0 flat space. Beta should be order 1 in flat space.
Yeah, if your gamma was not a unit sphere metric.
Yeah. So beta should be order 1.
Yeah. So now I will just related to what you said. There is not much choice, but I think we could allow gamma to be.
Okay. And so if we allow for these super rotations that Alok has discovered, then there is a choice.
But we don't mess up with asymptotic flatness. They're still asymptotically flat space times, right? Like the Weil tensor is going to 0. Yeah.
Okay, so as you can see, there is an enormous discussion about all this, and if you talk to 2 people working on this subject, they will have some minor disagreement on.
So gamma AB was the sphere S2 metric in de Sitter.
Yeah, gamma AB was the leading order S2. That this equation remains valid even in that case. And gamma AB was the leading order metric in de Sitter. And yeah. So the equations of motions are not telling us much. Equations of motion are only telling us that you must allow arbitrary boundary metric at infinity. So this is what it is telling us. U0 du dxa plus gamma AB. Gamma AB is arbitrary, so gamma AB maybe it's slightly. QAB is a better notation, not to confuse with the round metric on the sphere. So QAB dxa.
It is 5 on space. I mean, is beta 0 U or U0 A?
Beta 0, U0, and this actually what has come out is that you are allowed to have any arbitrary metric at the boundary. This is what has come out of this analysis. And this is this locally asymptotically distributed space.
Just like ADS, right?
Exactly like radius. Yeah, exactly like radius.
I mean, and to put it the other way, it was just saying that the metric on the boundary can have any non-normal.
Equations of motion will not fix it.
I'm just
equation of motion analysis cannot fix this.
And sorry, and in pure de Sitter, QAB was the round metric.
QAB is the round metric.
Was what? Was 0 and beta naught was 1.
Beta 0 is 0, so e power 2 beta 1.
Okay, thank you.
Okay.
Sorry, I mean,
So,
even in flat space, in flat space also Q is not fixed by equations, right? I mean, we make a choice that it's gamma. So I think at the same foot, is at the same footing, no?
Yeah, I agree. I agree.
In pure physical, beta 0 was 0.
Beta 0 is 0, U is 0,
U is 0,
and
yes.
QAB is round metric on the sphere.
There are no regularity.
The regularity conditions cannot be analyzed even in Fefferman-Graham gauge, so the same issue is here. Yeah.
sorry, so when you are saying that QAB is arbitrary, I mean, don't you have gauge fixing conditions on top of the equations of motion that have to be imposed?
Yeah, this is the next topic. So boundary gauge fixing.
Sorry, Amitabh, about Poincare's question. If you were to do it in perturbation theory around de Sitter,
yeah,
then you would solve it everywhere.
Yeah,
and then there would be no regularities, right? The solution would be in perturbation theory. Fine.
You will, yeah. In perturbation theory, you will use a Green function. Perhaps that Green function will give rise to certain regularity and certain.
Yeah. So it's only like a finite deformation that you might have regularities, right?
Yeah.
Sorry.
Also using your fluid gravity idea, one can try to integrate in the theta direction.
So the boundary R equal to infinity, I think she has already answered. Where exactly? What's that surface? R equal to infinity is where?
It's this diagram. So constant U lines are these. R equal to infinity is this surface.
I think R equals infinity. Poincare coordinates we have been called eta groups.
Eta groups.
Yeah.
Okay, so I think Somnath pointed out that this is too arbitrary, too crazy in some sense. So now this is where we choose the middle ground. Okay, so this is the boundary gauge fix. So this is new physics input that we are giving now. Because you see, if we work with this, we cannot. There is nothing we are learning because this is like Strominger's no boundary conditions. I plus free. If we work with this setup, then I plus is free. Theta is a function of U and X. U is a function of U.
If you work with this, you're getting the phase space of all gravitons. All fluctuations.
Yeah, no, but I want to talk about the energy of gravity.
Okay. Before that, though,
yeah,
this sounds like a very reasonable thing to do, right? I mean, just work with the full phase space of allowed linearized solutions.
Yeah, but then I cannot. Yeah, I mean, this is the reason I say the subject is confusing. It's not clear what one should do. If I want to talk about a notion of Bondi energy, this is why I started my talk like that. If I want to talk about the notion of Bondi energy, then I should do something else.
Okay, fine.
Yeah,
but just for the phase space, you might just stop it, right?
Yeah.
Okay, and one last question about this. I'm sorry to interrupt so much, but there's been all this recent talk by Subrat and friends about how the phase space is confusing. I never completely understood the confusions, but from this point of view, the phase space is very simple, right?
Oh, no. The phase space is simple, but there is no discussion of the compactness of the slice here.
Okay.
If you impose those things, then of course a lot of confusion will come in. Then you have to inquire Gauss's law constraints and things like those.
So then you satisfy the word identities of of all these isometries and energy. I mean, that's a nice thing, but it's not surprising because that's what one did in computing.
No, but there are other issues. Yeah, but this is a separate topic.
But I thought that was like somebody we should have solution. But okay, you have to satisfy some word identity.
Yeah, that's some few constraints on top of this, right?
No, but when there are compact slices, there is something called linearization and stability constraints. Those things need to be taken into account. They are like, so you suppose you construct a linear solution. That linear solution may not be a linearization of a non-linear solution. So that issue has to be addressed.
Yeah, I understand. You have to meet Gauss choice.
Yeah.
Okay.
You have to meet all the isometries must annihilate the states, right?
That happens even in QED, right? You put a charge on a sphere.
Yeah.
You can't put one charge. There are these small number of constraints. They give you some small cut down on top of this. That's what presumably happens, right?
I mean, what I can say for sure is if you construct the wave function, you have to impose the isometries and the word identities of energy momentum, by which I mean translational invariance along the path.
So Sandeep,
ask Subrat to speak on this.
Yeah. No, I've discussed it, at least he agreed with that statement.
So you think there are multiple solutions which are digital isometric apart from the same?
It's like as many choices as you can think of CFT. So I mean, you expand the wave function in terms of.
No, but just classical in terms of classical phase space. Can we find solutions which are?
If you don't put any particular conditions in the far past,
yeah,
and you asymptotically just do the analysis, the answer is yeah.
Because digital is the most symmetric solution, right? So if you demand that symmetry, then I was thinking maybe you just take that space up.
Okay, we can. I can show you exactly what the constraints are. It's really like ABS. It's not different conceptually.
Yeah. Along the line, I'm so sorry, but just because so much confusion has been around. If I ask the following, if I take linearized solutions, okay, let's say of a scale, not even.
Yeah.
And then I ask, for which of these can I solve the constraint equations? The Einstein constraint equations, but just classically. That may give some small cut down, but not a very large cut down. Is that right? Meaning, for which of these can I perturb the solution to a nearby solution so that the classical constraint is solved? You know, I've done this analysis once for non-abelian gauge theory, and there's a small cut down. And the small cut down is you get gauge theory, gauge signals. I wanted to make sure that the answer here was yes, in case you happen to know.
No, actually, I don't know. I just know that there are these linearization stability constraints that needs to be taken into account. Now, I don't know how restrictive these constraints are. This Subrat should answer. I don't know.
Is that the same question as finding solutions that are symmetric with SOT, 1 symmetry?
It's not clear to me that is.
Because that constraint is the SOT plus 1 invariance only.
Yeah. I was thinking something just more mechanical, which is just take a linearized solution and then ask for which of these are they near to some nearby solution that solves the constraint equations. And all such things belong to the phase space. So
I mean, it's that plus you have to make sure it's invariant under the de Sitter isometry. Plus, there's a little bit more in terms of incorporating the gravitational pattern. I mean, which is a statement that asymptotically you meet the energy momentum constraints of the boundary C.
Right. These energy momentum constraints are the constraint equations, right?
Yeah. No. I mean, the constraint. Okay, depends. Which constraints you need?
Yeah. Gauss law.
Yeah.
So you can take the Gauss law constraint of gravity and integrate against this isometry. The isometries of dispersions. Those give you some constraints. The leading order in G Newton, those are just
okay. Yes, they are the residual isometries. That's right. Yeah. The Hamiltonian and momentum constraints integrate against.
Yes, it seems to me that there's a clear mathematical question to see which linearized solutions can be perturbed to satisfy the constraint. Doesn't seem like it's a very hard question to answer.
The linear order in G Newton, isn't it just a statement about having like de Sitter invariant states on QFT on this space-time?
Could I just talk classically? I've got a classical scalar. And now Einstein's equations have to be obeyed. I'm willing to perturb, I'm willing to change the metric to it, but it should be possible to get some nearby solution.
Yes.
Okay. And there are some global constraints that will stop this. So the question is, for which part of the space does this global constraint? And maybe what
I think classically it's just that the solution has to be de Sitter.
Now that sounds very interesting, right? Something there are no solutions.
Yeah, that's what I was saying.
No.
So then how do you get around this? What do you have?
No. You can take solutions and you can smear them over the isometry.
No, but that's a quantum.
Yeah, classically.
No, classically you can smear.
What do
You have classical generators that act on the smearing. I mean, you take a solution, you have the classical isometry generators. Okay, so suppose you take, this is an aside, I apologize.
No, please.
Okay, let's say for a moment, we take a scalar thing, okay? Now we turn off G Newton just for a minute. So it's in the Sitter space. We have a solution and it doesn't meet the conditions that it's invariant to the SOT. but there are well-defined generators of those symmetries. So you act on the solution with those symmetries. If you smear it, yeah, it's a non-compact.
No, that's not. I mean, smearing is a quantum mechanical concept, right? So adding things.
Group generators. Okay, group.
You at the end of the day produce the solution.
Yeah, yeah.
By smearing, but then you will just constant.
Yeah.
If you take a lump and smear it, meaning if you just then you will just get constant.
Yeah, the only phi of x that is invariant is constant.
But quantum mechanically, of course, right?
That's what Surah was. Yeah, that's the approach Surah and friends, etc.
Okay.
But classically, I don't see how exactly this would come out. Even if a little bit of hint in that direction would be useful.
I see. You say there's a disconnect between the quantum and classical. Okay, I studied in the wave function. I agree with you. Okay.
See, the conclusion is that quantum field is possible.
But I mean, you can have a boundary condition which respects the formal invariance. So, I mean, a boundary wave function. You really mean? Okay, I don't know. I mean, you can certainly write down. I'm sorry to have such a poor knowledge, but you can certainly write down 2-point correlators satisfy, conformal invariances. In theory. Okay.
So why did you want to insist on classicals?
No, I think it's very weird that the classical phase space is empty with a quantum solution.
You should quantize that phase space to get the quantum space.
No, but asymptotically, if you quantize, there's not an issue. I mean, asymptotically, he's doing the quantization.
Yeah. No, the question was the phase space empty or not? Classically. Somehow, I intuitively feel it's not empty. Analyze it, I don't know the answer.
I feel otherwise, but I don't know any hint in that direction would help.
Yeah, I know.
I think that's not a solution.
Actually,
your analysis is a non-compact space.
Yeah.
So,
but I can say
it could be that the compactness is rather destructive.
Yeah. So all this discussion is really related to compactness of de Sitter slices. But I maybe just make a comment that relativists have also analyzed such constraints on T3. Like if you consider gravity on R times T3, 3 torus, and you ask what kind of constraints you will get, this question people have analyzed.
Yeah, I mean, the way gravity absorbs energy is by curving energy. Okay, it's not that simple that you just put energy and there's no way. That's how we get the ABS energy, right? And that kind of thing, I think.
So it's not an isometric question.
I feel it's not just.
Not just solving constraints, you can solve it otherwise.
I feel you will get it.
I see. Okay. Yeah, because we don't have any states.
Maybe then it's not right. I don't know. Okay, just 1 minute. But maybe you can't do it in G Newton waves. There must be something. I don't know. I see your point. You can write the quantum solution.
Okay, so as was suggested,
usually interrupted before solving a classic quantum problem to solve the classic.
And this smearing also needs you to move a different norm, etc. Maybe it's a great engineer. So
sorry, Amitabh, we should have a discussion.
Actually, a version of this discussion really comes up in flat space at space like infinity also.
And do you have any?
We put extra boundary conditions. So the way we do this is that is a separate discussion. Yeah. Okay, I am also getting digressed. So flat space at space like infinity, Alok must have told this. I mean, we can write it as hyperboloid. And on this hyperboloid, when you solve wave equations, first order equations are linear, but second order equations are non-linear. And second order equations will have some constraints of the type that we are discussing. And those constraints need to be met, otherwise.
Constraint meaning coming from non-linear scaling?
Linearization still with constraints. Okay, so as somebody was suggesting, we should put some boundary gauge fixing in order to make progress. And there are 2 boundary conditions that people have discussed. One that I will discuss in the talk in the later part, and one which I will not discuss. So this is the Brussels group. So this is beta 0 equal to 0 and UA equal to 0. So they say that we choose our universal structure by setting beta 0 to 0 and U to 0, and we work with only the QAB. QAB is arbitrary. So this gives sufficient universal structure to talk about normal to constant U hypersurfaces and asymptotic symmetry, scaling vectors, things like those. The other boundary condition was crucial. Molta, and also the most recent paper by Bonga et al. These boundary conditions, so I must say these are very well studied.
No, the other one is crucial.
The other ones I like a little better, but they are not so well studied. But actually, nobody knows which one is better. So here the boundary conditions are that QAB is gamma AB, which is round metric on this sphere. And UAB. UAB. Okay, so there is a clear difference.
Just a question. In the T3 case, which passingly mentioned, almost all the phase space survives.
No, that analysis has not been done in this language. That has been done in the original linearization instability constants. The same authors. Higuchi.
I have a question. Like, I mean, does this gauge fixing in any way mess up the fact that the number of degrees of freedom of the metric should be 2, or does it ensure?
No, it does not. It does not, because in the first case, QAB is arbitrary, so there are 2 degrees of freedom. In the second case, UA is arbitrary, so again there are 2 degrees of freedom.
I see.
Yeah. Okay, so these are the 2 setups that people have studied. Perhaps the 2 setups are related. Nobody knows the answer to that question. Perhaps the 2 are equivalent. Nobody knows like how to relate the 2. I mean, some set of papers analyze this, some set of papers analyze this.
What did Ashtekar and all find when they put in the Bunch-Davis conditions? Just did they get one of these?
No. So
that seems the most physical. I mean, you work.
So a paper will come out in a few weeks by people in the audience, and they will explain some of those issues.
Okay. Thank you.
Yeah.
So this is roughly half of phase space. Phase space was 4 fields.
4, yeah, you're right.
And now it's 2 fields.
Now it's 2 fields, yeah. So in one case, I am killing these 3 functions.
Yeah, why was it?
That's not the language in which I have thought of, but these are the, maybe one can. I think beta 0 to be 0 is perhaps not that important.
Yeah.
Perhaps. But the main point is that we are killing these U's, and here we are killing the dynamics in the Q.
And the full phase space was U's and Q's. And U's and Q's are not canonical to.
No, they are not canonically conjugated. The canonical conjugation relation was like delta G wedge P. Yeah. So boundary stress tensor in the boundary metric.
And at some point you tell us what that is.
Well, this was my plan, but I don't know if I actually let me try to speed up a little bit.
So on the left, QABs are like the 2 QABs.
Yeah.
Will be like the magnetic guys, and their dots will be like the electric.
Yeah. Actually, they are all magnetic. They are all non-normalizable, because these are the boundary metric components that I'm gauge fixing. Boundary metric is all non-normalizable. So beta 0, 0, non-zero, these are all sources in the ED6.
So whatever are the sources are what you call the magnetic things, and their dots are the.
Like they have to look myself. Yeah, you're right. They are the magnetic things, because electric ones are the normalizable. Yeah.
Amitabh, look, as in the ADS case, asymptotically locally ADS is the first guy or the second guy? Is that? Is this?
Yeah. Asymptotically locally ADS has all these things turned on.
I see. And you can't divide it into Brussels group and nothing is frozen. I see. Okay.
Again, if you want to talk about, this is your favorite topic, if you want to talk about Robinson-Trotman spacetimes,
yes.
talk about the energy loss of energy loss coming from Robinson-Trotman, then perhaps you have to do something similar.
Okay, thanks.
So when you're talking about the phase space, does the EAB correspond to the momentum, canonically conjugate momentum for the GAB or something? Because I mean, in Yang-Mills it does, right?
You can say in that language. I guess you can say in that language.
I see.
So what is the plan now? Shall I continue? Okay. So so when we do this analysis,
there's another problem tomorrow. So like you can do one as well.
Okay. So when we do this
analysis, almost no talk ends before one.
Okay. So when we do this analysis, as in flat space, the most important quantity to work with is the correction to metric on the sphere. Here also it comes up. So it just so VAB is QAB plus CAB over R. So this is the quantity that is the most important thing to worry about. And perhaps this is the most important equation in this subject. If I am writing only for this case, I am not writing for that case. Similar equation is there in that case also. So the key point here is that in flat space, CAB was the independent field. When you put lambda equal to 0, this equation is 0, and U was 0 in that case, so 0 equal to 0. But when lambda is non-zero, we allowed UA to be arbitrary, and this completely fixed CAB. So the shear tensor is completely fixed by the UA0. And this equation has been discovered over and over by many people, but it was emphasized a lot in this paper. So lambda equal to 0 versus lambda not equal to 0 are very different, essentially because of this equation. CAB is a derivative. Okay, so in flat space we call CAB.
Can I just repeat what you said about lambda equals 0?
Oh, so if you I have removed that part. If you look at the boundary conditions I put in flat space, the boundary conditions were UA 0 equal to 0.
Yes.
So if you put UA equal to 0, the right hand side is 0, but you are in lambda equal to 0 also, so the equation is a 0 equal to 0. Okay. When lambda is non-zero, then this equation, multiple ways you can think about it, but perhaps the best way to think about it is that CAB is completely fixed in terms of U. CAB is algebraically fixed in terms of U. So CAB is a derivative. Okay, so now people who are very familiar with Fefferman-Graham expansion, they will not find this surprising because CAB is the 1 over R term, which means it's a subleading term, and subleading term is of course fixed by the G0. Okay, so
the normal Fefferman-Graham expansion is also the genuine new data, which is the normalizable.
That will come. That will come. Yeah, but this is only one order. I have gone only one order. Yes. Now let me just answer Shiraj this question about Fefferman-Graham discussion. So so what I can do, this is the calculation we are working on right now with Sitinder Kashyap, Jahanur, and one student Harsh. So Fefferman-Graham form of the metric is right flow. So we are gamma AB is G0 AB plus rho times G1 AB rho square times G2 AB rho G3 AB. So let me first review Fefferman-Graham because like younger people may not be familiar with it perhaps. So in Fefferman-Graham discussion, what happens is that if you analyze this setup and analyze Einstein's equations order by order in powers of rho, then what you find is G0 is arbitrary, G1 is 0. This is in 4D. G0 is 0. G2 is algebraically fixed in terms of G0, and the relation is and then G3 is arbitrary. And this is called the boundary stress tensor in ABS-CFT. So this is the structure of Fefferman-Graham expansion in 4 dimensions. G0 arbitrary, using Einstein's equation, one sees that G1 is 0, G2 is fixed algebraically in terms of G0, and G3 is arbitrary. So one can ask.
And 3 is because you're in 4 dimensions.
Yeah, we are in 4 dimensions. Yeah. So one can ask, now I have these Bondi expansion. I convert my Bondi expansion into Fefferman-Graham expansion by changes of coordinate and ask what is happening in that setup. Okay.
Why couldn't one start in this coordinate to begin with? Why couldn't one start in this coordinate to begin with?
In this coordinates, G0, it's natural to take G0 to be arbitrary. But from this Bondi discussion point of view, I want to do some partial gauge fixing. So that partial gauge fixing came out only when I analyzed things in Bondi coordinate. And once I know what partial gauge fixing I have to do, I can convert.
But what is this qualitative difference between? Is there a qualitative difference between?
No. No, there is no qualitative difference. I mean, these equations up to minus signs, they are exactly the same equations. Yes. Yeah. There is no difference. Okay, so I hope the logic is clear now. Einstein's equation will tell us trace of this is 0 and divergence of TBC. So maybe I will just say it in words.
So you said that you could motivate the boundary gauge fixing only in the Bondi coordinates.
The literature could only come up with a recent, with a recent proposal that way. Because in Fefferman-Graham gauge, people have analyzed this over the last 20 years and there was no proposal about how to define Bondi energy. That question is also valid, whether we need Bondi energy in De Sitter or not. That question is itself valid. But suppose I insist on finding such a notion, then I should do something.
Okay, I'm sorry to slow you down so much, but just I wanted to do some counting.
Yeah.
So boundary metric has 6 components. It's
3 into 2
by 3 into 4 by 2, yes.
Yeah.
And then we can do boundary diffeomorphisms.
Boundary diffeomorphisms, yeah.
That gets rid of 3 of these. Is that right?
Yeah, 3 of them.
So that's 3 left.
Yeah.
And then the normalizable mode.
Yeah.
Once again, there will be 6 things obeying a stress tensor conservation equation. So once again, 3 left.
And the trace also.
And the trace. So total 5 functions in your phase space. Is that right?
And actually, I have done this counting carefully. I don't have it in my notes, but I can.
But roughly, this is correct.
Yeah, this is how it is.
Yeah.
In Fefferman-Graham.
Yes, you should take that away. Interesting. I don't know. It should. Are the rules that we should take it away? Yeah, that would make it 4. Yeah, that matches Gravitational, which would be nice.
So phase space cannot have 5.
Yeah. Well, it's 5 functions.
5 functions.
It's not 5 now, but I agree.
Even otherwise, we are saying some function could be self.
You guys have a subjective form, right? Which F with F prime or something.
Yeah, so the function itself can scale.
Yeah.
Okay, so now let me write one or two equations just to illustrate this point. So if we use, if we solve Einstein's equation order by order with the boundary condition that beta 0 is 0, then we find that beta 0 is 0 by choice. The 1 over r term is 0 also, and we only find 1 over r square term, and it is given by the square of the shear tensor, and this sort of ties up with the fact that G1 is 0, G2 is Ricci scalar, and so on. So, like when we analyze the equation for the function v, we find that this is divergence of u is u times r, and so on. For all fields, like u is 0. Minus 1 over t r squared dv, and QAB is gamma AB, because I have chosen the boundary metric to be the sphere metric to be the round metric on the sphere. And
sorry, you first solved with Graham-Fefferman and then we moved back to Bondi?
No. I'm doing two independent calculations. This was just a review. I was reviewing the Fefferman-Graham expansion. Now I am back to my calculation. So I have Bondi coordinates, Bondi expansion, and just analyzing equations of motion. And when I do this careful equation of motion analysis, then beta 0 is 0 because this is the boundary condition I have chosen. Beta 1 will turn out to be 0. Beta 2 is given like this. Similarly, this term is this, and the next term is given like this.
So just stand out for a minute. I was with you till here. That was Fefferman-Graham.
Yeah.
And here what's happened?
So this was a review. My original plan was to analyze equations of motion in Bondi coordinates, order by order in R. So I'm just solving those equations now. So when I'm solving these equations, this is what I'm finding. And we have computed these things to sufficiently high order, and we show that these things are perfectly consistent with the
you do a transformation
to coordinate transformation between these, and these equations give us the mass loss equation and angular momentum loss equations, because this will T A 0 equal to 0 will give us the equation like m dot. We can do a lot of things, and the other equation T A equal to 0 will give us actually this is some variable I have not introduced, but this will give us equations for the angular momentum aspect, and m dot equal to something and n dot.
So the energy momentum tensor is gravitational, right? I mean, it's a gravitational energy momentum tensor. Is that correct?
This CMI is the boundary stress tensor. Brown-York boundary stress tensor.
Yeah, I mean it's composed of the metric. That's what I'm saying.
Composed of G3 actually is equal to G3. TAB is equal to G3.
Yes.
Okay, so conservation laws give us flux formulas, and what it is telling us is that we can write down equations this type. So this is perhaps the place where I will stop.
You don't need to stop so soon if you have more material.
Just to understand, sorry, this Bondi analysis, sorry, we will step up briefly. This is just the general analysis. Then on this you impose whatever middle ground you want.
Yeah. Middle ground will give us these such equations.
No, I mean here you made no choice.
No, I have made because okay. Order one term is 0.
Okay. Do you need that choice? But then you allowed U to be anything.
Yeah, because that is what I wanted to allow.
And QAB also.
QAB, this is round metric on the sphere. This I did not want to change.
It is not fair.
This I had not also understood. So then now you can translate your middle ground and then to Graham-Fefferman.
Yeah, that's what we have. That's what you did. That's what we have. Yeah.
That is some restriction on the induced light, right?
The restriction on the induced.
Yeah. Just one question. I thought the original thing that I was thinking for that there are no timeline isometries.
Yeah.
Sure, you're using one of these isometries.
Yeah. No. Okay. So yeah. So you see, now I have a middle ground. So middle ground means that I have a foliation of the boundary metric in which the cross section is round metric on the two sphere. So that foliation I can use to define normal to that, and that I can pull in the
pulls back to some time-like isometry.
Yeah, that actually pulls back to time-like isometry. Yeah.
Because
then
that situation will be conserved. Right?
Yeah, then U is actually a perfect isometry of de Sitter, and that's what it becomes in this case. Okay, so once I have done this kind of calculation, then this is what I am able to do. So suppose I have a slice here and slice here in de Sitter. I can define energy for this slice, ADM kind of analysis. So this will give me some E2, this will give me some E1, and I know.
So just to understand roughly, these are sort of like your slices going in along constant R. No, this is some other.
These are just random slices.
This is random hypersurface.
Yeah. In flat space, they will be like so. Okay. Random hypersurfaces I'm drawing. I want to talk about the notion of energy loss. So that's the reason.
So this is like Bondi energy.
Yeah, this is like Bondi. So E1 and E2 will give us Bondi energy. But since I have these formulas from coming out from this analysis, I will be able to write an equation which is E2 minus E1 equal to integral of dE du over delta E.
These slices are closed, right? What is how they go?
That question, I mean, so that question is slightly difficult to answer in these. Yeah, okay.
You want to just take them back?
Yeah. No, R times, so my boundary metric is R times S, topologically R times S2, and in de Sitter there will be some completion of such spacing, and they just stop at the
smoothly pinch off.
So they will. In the S3 case, they will smoothly pinch off. In the R times S2 case, there will be a point.
There's a word line.
Yeah, word line of the, yeah.
Static observation.
Yes, yeah, something like that.
I'm really sorry, just to get on my inflation. What's the difference between capital A and little a?
Capital A, this is the standard GR notation. Capital A is the indices on the sphere metric, on the co-dimensional.
Yeah. So for you, it's two-dimensional.
Yeah, two-dimensional cross-section.
Yeah.
And small a are ADS-CFT notation, where small a are the coordinates on the
all of it. Okay, thank you.
So small a includes U. Is that right?
Small a includes U and A. Yeah.
So U, theta, and phi are small.
Yes.
Small a.
Yeah. U and capital. Yeah.
So Amitabh, can energy not leak through that hole? Can energy not go away through that hole?
Actually, this is also a tricky question. I don't know the answer to this. I have done the whole analysis or the whole discussion in the literature has pure gravity. So indeed, there is this issue that the particle will come and hit the boundary. How to do that carefully?
Just why not just do it for global de Sitter? Compact spatial slices. That adds some manipulation.
Well, I want my U vector to be very special. If I don't have partial U, then I will get stuck. Perhaps.
Amitabh, can I have a comment? Yeah.
Yes.
So basically, R cross S2 is the 2-point removal from the S3. Because 1 point you remove from the corner of the Poincare pair, then other point you remove from the left corner. So this is the 2 point you remove in the Bondi. So, So this is basically 2-point removal from full S3.
Yeah. So what Sandeep is asking, can we not do this for S3 itself? Will that?
Yeah, I think S3 has people studied, but S3 you cannot have the gravitational radiation, right? Because
So why not?
I mean, the answer.
I mean, one can analyze, but yeah, but my feelings is that on sky, if you consider S3, I'm not sure you will get the radiation or not.
No, I mean, certainly you will have radiation.
Yeah, you can get, but yeah.
Is the point that the radiation cannot have anywhere to go?
Yeah, I mean, S3, like, you don't have any boundary, right?
Yeah.
So you cannot, I mean, I think it is.
Then to turn it around, or that go on.
No, perhaps there is some discussion required for the. Yes.
So I missed.
Amitabh, just a small question. The U0 depends on small u also, right? As you said, preferred direction that you have. So yeah, that one. So what is the fall off condition on U0 in U? Is there something required? Or,
yeah, that is an independent discussion. At least the Fefferman-Graham discussion does not tell us any boundary conditions in the U direction in this case.
Okay.
But
thank you.
The technical point, like some people have discussed this boundary conditions at space like infinity. So perhaps that is Kelly-Marolf paper.
Okay.
Yeah.
So
thanks.
Between you and the boundary, you're moving along that R. Is that me?
No, so this is U direction.
Okay,
this is U direction, and R going to infinity.
No, I mean this. I mean that R times S2 that R.
Oh yeah, R is like this, and cross. Yeah.
Okay. So I guess Alok is trying to get at this whole. Maybe you can say that the flux does not go through there. I guess. Right?
Flux. Sorry.
I mean, if you say that there is a boundary condition, this fall off condition there.
Yeah.
My question was the finiteness of total flux, exactly. I mean, that must impose some naively condition U, right? Yeah.
So as in the asymptotically flat context, this has been discussed a lot in the last 5 years.
So I think embarrassingly enough, I think I missed your main point.
Yeah.
How did your restriction allow you to define an energy that you couldn't without the restriction? I missed that. Sorry.
No. So yeah. So actually, so now I have boundary metric. That boundary metric has a special foliation where the cross section is round metric on the S2.
Okay.
So that special foliation gives me a normal vector, and that normal vector points in the U direction. Those are
just all this on the boundary.
On the boundary.
On the boundary, it points in. Yes.
So now I got a U vector. Then I push this in the bulk.
How? Some parallel transporter. No.
I mean, technically speaking, what I analyze is the notion of asymptotic symmetries with this definitions, and then I will find that partial U is part of my asymptotic symmetry. Okay. That is, there will be a asymptotic symmetry which will, when pushed to the boundary, will become partial U.
Okay.
Your U is still moving along the boundary. Right?
Along this direction.
Now, why not just to ask you, okay, compute the Brownian stress tensor and take its component along that.
That's what it is. That's what M is. That's what M is.
So that's reasonable,
No. But you have to give me a U.
I'm missing.
That's wrong. So we needed.
What I'm saying is he has chosen to break the full S3 symmetry by choosing a U direction.
Yeah.
But after that,
after the cycle was a Brownian. Yeah.
Now, I heard it. What happened to Onkar's question about the isometry? Is this some charge under some isometry or not?
Okay, so there are 3 papers on this subject. All 3 papers have different answers. So the issue is not settled.
Isn't it that you still have the isometric group of the sphere, but you remove 2 points?
So so there is one paper which claims that the symmetries are isometric groups of the sphere and partial U. So this is the symmetry that.
I meant of the 3 sphere with 2 points removed.
Yeah. So that is isometries of the S2 and partial U. Just this.
Okay.
So I'm so sorry, but partial U is one of the Just take de Sitter space. Partial U was one of the isometries of
one of the isometric, yeah. Time translation. Actually, in normal language, this is just
it's moving from this direction on the cylinder.
Yeah.
Is it
angular
oscillation? Just the wireless.
Yeah, then it is scaling.
Amitabh,
yeah. I will write the formula. I have the theta delta.
I think it's a ground line. That's right. It might be correct.
Space of V.
You reach the space, and what in ABS should be.
Now, will this be an asymptotic isometry for all of your metrics in this middle ground?
Yeah, this is so all the three papers agree on this point, but they don't agree on what are the other isometries.
But let's put those aside for a minute. Okay. Now, if you had gone away from your middle ground, would this not have been an isometry? You would not have been able to find some isometry.
Yeah.
Is that the point?
No. So this is what Samir et al. Analyzed in the 2000s and 2010 or so. They find that in that case, the diff I is the full asymptotic. The asymptotic symmetry group is diffeomorphism, all diffeomorphisms of I of the boundary.
That's what would come out of the constraints, I think what I'm saying is the Brown-York stress tensor would be conserved. With respect to all the diffeomorphisms.
But this is what I'm saying. Like if you allow that setup, if you work with, then you cannot come up with a good notion of energy.
Yeah, because there's no preferred
direction. There is
no
preferred direction.
No, I agree with you. You just have what you have are representations of the angular momentum on the free sphere. Yeah. That's not good enough. Just characterize states by SO4 representation.
You mean you are saying that my symmetric. So this issue is not settled. This is the reason I'm saying there are three papers and three papers have different asymptotic isometries. So this issue is not settled.
Exactly.
But just to ask you, since you have talked so much about it, studying this. Okay, in global coordinates, you have a S3. And you have the generators of the isometries of the S3. And you characterize states in terms of those.
This is the proposal of most recent paper of Banga Boomster in Paris. This is what their proposal is.
Seems like the most. I mean, just to ask, what we were thinking was if you just take global coordinates, you have a boundary S3. And then, you have the isometries of the S3.
Yes.
Which is SO4.
Yes.
And you can characterize states in terms of forming representation of the SO4.
Yes.
So you just characterize them in terms of those castings.
No, what was confusing me even about this was this, that in the earlier discussion, Amitabh went through this discussion about how even the boundary was very floppy.
Yeah.
So it felt unlike ADS, where normalizable states differ in the bulk, but all become the same at the boundary. Here, it's not even like the round S3 plays a very special role.
The round S3 plays a very special role.
Because at generic point and phase space, even at infinity, there's no round S3, right?
Yeah, there's no round. That's correct. That's correct. If you turn on the most general normalization, but you still have a conserved quantity. I think because you have those asymptotic diffeomorphisms.
Which knows about the round S3 as being special somehow?
No, it just knows about moving.
Yeah, they don't know about.
They only know about moving here. Okay. They only know about moving here.
So then, so have you managed to get an isometry by restricting to those solutions that will have an asymptotic isometry? Is that what you're doing?
This issue. This is what I am saying again. This issue has still not been settled. Like there are three papers which analyze asymptotic symmetries with three different boundary conditions, and they find different answers. The most recent paper proposes that in the R times S2 setup, the asymptotic isometries are R times S2.
But if your stuff at infinity goes far away from R times S2, it seems to me that the only way to get the isometries of R times S2 is to tune your phase space to those that have an R times S2.
This is what
gravitational waves around this is or this planar.
This will not be.
Yeah, that's what I was saying. I mean, what I was saying was for small.
This I agree with. If you're doing small fluctuations around some, but he was trying to do more, right?
No,
Yeah.
You know, just to say, if you take black holes and this setup, you can still characterize them as representations of S. I mean, because they still are asymptotically dissimilar.
Correct. They have to be genuinely.
So I'm just saying, even strong gravitational objects. Plus
they fit into Dirichlet boundary conditions.
That's also one of the questions. So why is it that, as you were saying, this black hole, etc., you always look at, one always looks at this asymptotically dissimilar geometries.
At least for black holes, that's a property, as you were saying. They're just asymptotic. It's multiple. They're like division.
Just because you don't look at the other ones.
Yeah.
Okay, I don't know. You're right. Maybe this is what people have written down as black holes.
But
The standard black hole solution.
Naive way of saying all this is that, there is a full ADM formalism, but if you want to just read the mass of the ADM, mass of the black hole, you just expand in powers of 1 over and you get the mass.
Maybe Abhijit is saying there should be more general solutions.
Yeah, so
that's probably
that is what it is.
I guess you can fix that boundary condition. Right here, you just can.
And your whole phase space is with those fixed boundary conditions.
Yeah.
Okay, so for me, this is a natural place to stop because I have discussed the Fefferman-Graham part. And so there were a lot of questions about linearized gravity. When we do linearized gravity, there are a lot of other subtleties which I will discuss.
Thank you so much.
That was really great.
We had many questions, but if there are more, Zoom audience first.
Yeah, so I have this question, like when you're talking about asymptotic symmetries, what happens if you consider the BMS group as well? As in...
So as I was saying, there are 3 papers with 3 different proposals. So one paper is R times S2 isometries, other paper is BMS-like isometries, and other paper is generalized BMS-like isometries. It's not clear how to reconcile all of this.
I see. Okay, thanks.
If there are no questions on the Zoom, then maybe audience here can ask.
I want to say one thing, and I'm really, really sorry, please excuse me, which is to go back to this discussion of the S3 and how the quantum works versus. The quantum, and I must apologize for my poor knowledge. Your points are all well taken. One should know the classical system much better. But still, the way the wave function works is you specify it in terms of the boundary, non-normalizable. But okay, now you look at the action of the isometric group. And the way it works is it changes those boundary conditions. See, because they correspond to the values of some scalar fields and they change. So that absorbs the change, So where I'm going with this is, it suggests that one shouldn't think of the classical solutions as independent of the boundary data. It'll then relate to one. Could it be that it works like that? Suppose I gave your initial data and I started solving the classical, because that's also a spatial hypersurface. Okay, I leave the normalizable mode free. That I could specify by boundary conditions on the Poincare horizon, if you like. This is actually how the quantum calculation. Now I start solving, I get something. And if I were to do an isometry on this, it will change the boundary data. Then I'll generate an entire family of symmetries. See, that wouldn't be so puzzling.
Exactly. And the first point in your thing is like the classical equations, right?
Yeah. Please say.
No. Like, I was just saying that also suggests that the classical phase space is rich.
That's what we are starting with. We are just changing the boundary data to change the solution, which you would have specified that way. So I'm just saying, if you think like that, okay, it's not so strange. That's what the quantum theory is doing.
Yes, sounds good.
How exactly does this so this gives a classical solution, but it's decision.
No, he's saying that no classical solution is incident. But the condition of disappearing variance is a quantum condition. It's obtained by smearing over the solutions which were
exactly. It relates one solution to the other. So what it says is the wave function or the amplitude for one particular solution, one value asymptote is related to it.
I see. Oh, this I see. Okay. So this is the thing where you don't actually pose the generators and annihilate states, but you actually think of states as being like class equivalence classes of
Covariance.
Yeah. So Gupta law versus Yeah. It's like if you ask, is there a classical state which is an ideal state of translation for a particle? The answer is no, right?
Oh, that's such a great answer.
What's the classical
Position of a particle.
But eigenstates, it's very.
I say no. I mean that has a definite. It
has a definite location.
Take Poisson bracket with the momentum generator. Take any point in phase space. Does that have an equation that point in phase space gives you back your point in phase space? Answer clearly no. Okay. Quantum mechanically, it's clearly yes. It's either pi p dot x. It's a smearing over these classical solutions. I think that's sort of what's going.
Yeah, you can integrate over the symmetry orbit in quantum mechanics because there's a linear superposition. Classically,
exactly. That's why it's possible to have dissident varying states quantum mechanics.
Yeah.
Even though it was not classical. Just like it was possible to have zero momentum states quantum mechanically, even though it's not classical.
So it's not a quantization of some invariant.
I don't think it is. I think that as something saying, you generate a phase space, and then finally the quantum wave function
you project
will be that smeared part of that.
Gauss law is only quantum mechanically.
That Gauss law. But even classically, there will be some cut down from the fact that the constraint equations have to be satisfied. That will be like the condition you cannot put a charge. There will be some cut down, but it will be a small thing.
What did you say in example? What will this cut down? Because it seemed like
you can do anything. Maybe there's no cut down. Maybe it's gravity so fluffy. The sphere getting flat. I don't know.
Then this goes back to what the kind of thing that first consider quantum states and then sphere.
Yeah, I mean, but the end result is that if you do classical mechanics, you land on your feet.
Oh, wow. This is what I mean.
Because you have your classical phase space, and then the final quantum state is some appropriate stuff of that.
Space is not obtained by imposing constraints.
No. Okay, it's some projection of that, but it's a small projection. Because you can take any classical phase space and smear over it again. State. You can take a very complicated state, classical. However complicated it is, you do something smearing operation, you get a quantum invariant state. So this is very rich. This is more or less a one-to-one map between classical and quantum problem. Seems to me. So, I'm sorry, I'm probably saying something.
When you're considering quantum gravity, shouldn't you consider the fact that you need to consider the full effective action?
We can hear you. Is this a question for me or for Shiraz?
Yeah. I mean, as long as you're discussing quantum mechanics or the quantum theory of gravity, I mean, shouldn't you, when you're considering quantum gravity, shouldn't you consider, instead of the Einstein's action, the full effective action?
What is, sorry, who was the question addressed to?
Anyone can answer.
Abhijit will answer.
Yeah, well, I think this discussion was, just about how you would go about quantizing the phase space.
Given a classical phase space, how we go about quantizing, not necessarily discussing action.
Yeah, I mean, the entire thing, this phase space business can also be couched in terms of the effective action, right? I mean, if you consider, for instance, the canonically conjugate momentum for the field, then, instead of just the normal thing, you would have corrections, and even the metric will have corrections. So I was just wondering.
Depending on the Hilbert space, not computing quantities in that. Just the quadratic theory. What are the consequences of the quadratic theory?
Yeah. So what I'm saying is, I mean, if you want to do full quantum gravity, shouldn't you consider the theory beyond the quadratic approximation? That's what I'm asking.
Yes. Okay. Yes.
I think we agree with you. One last question.
Yeah.
Your cut down was on the non-normalizable.
Non-normalizable.
Does that imply a similar cut down on the normalizable?
Not that I know of. Not that
But
I
then
know
how
of.
does PQ work? Because you should have as many P's as Q's, and I thought normalizable was Q and was P and non-normalizable.
Okay.
Sorry, what was the question? Yeah, it seemed like that.
No,
so that's not sorry.
Yeah, his question is that in my earlier equation, delta G was conjugate to TAB. Now he's saying that you have cut down delta G. So correspondingly, you have cut down TAB. And indeed, that is true because TAB in the end is written in terms of only these C's and other things. It's not a.
I thought you had independent Graham data.
No, that was the Fefferman-Graham discussion.
Yeah.
Now, when I went to Bondi variables, so TAB is constructed out of expansions of Q, U, and C. I mean Q, U, and beta, beta 0 or 0.
Correct.
Q and C, yeah, Q,
yes.
Q and U, yeah.
But the expansions in 1 over R.
1 over R.
Yes.
But it's only constructed out of that.
So there's some independent data in that at some point, right? And you only constrain the non-normalizable part.
Yeah. I think the independent
at 1 over R cube or something like that, then you have to do some new specification. That's the normalizable part. I was wondering about that.
Okay, I will answer. I will think about this question. I have not yet.
It's probably very stupid.
Yeah. No, I think these are the variables. M and NA are the.
M and NA, sorry.
Okay, I will think about it. Yeah. No, I think this question can be answered. Yeah. No, but I think the naive answer to this question is that when we do this change of coordinates, the TAB we will get is not an arbitrary TAB. It's constructed out of initial C and U and so on, and then of course new data will enter.
Yes.
U3 will enter. The third component of this, and the fourth term here will enter. Gamma, C, D, E. So
yes, good.
E term will enter.
So now already that's three new pieces, right? And some beta term also maybe or no?
Beta term will enter.
Okay, maybe it doesn't. So but that's already now more than you had up there, right?
The traceless condition is there.
Oh, so okay, fine.
Yeah, I have to do the count.
Okay, fine.
Yeah.
Hello. Hello.
Yes.
Hello, Amitabh.
Yes, yes, Shriji. Yes, I can hear you.
So one question. So as you said that there are three different answers to this question, that what is the asymptotic symmetric group of asymptotically de Sitter, right?
Yeah.
So as you said that there is a global BMS, a generalized BMS or some other notions are there. So would it be right to say that people are still finding out the appropriate boundary condition or foliation so that they can come up with the most general or answer, I mean, to this question, right? Is it because in asymptotic flat space also there are these ambiguities?
So there are multiple boundary condition, multiple proposals. The way I see the literature is that again in de Sitter, multiple boundary conditions people have proposed and multiple proposals they have. This is how I see it. At this stage, it's difficult to say which one is better, which one is more.
So is there an analog of that? There is a universal structure at the boundary.
Yeah.
And there is a symmetric group that preserves it is something similar. So is that the most general one, or people are finding something different to that?
So the Brussels group indeed they call this lambda BMS. Lambda BMS has both super translations and super rotations. But the other people do not necessarily agree with that. They find different. But their setups are also different.
Okay.
Just to say, I mean, if you just work in global slices for a minute,
global slices.
and again, I'm really sorry, I'm putting it in terms of the quantum wave function. Please excuse me. Then, what happens is instead of the conservation of the stress tensor, Brown-York stress tensor, you get the analog of that, but just that the other fields which are taking non-trivial boundary values have to transform. So in other words, the way the word identities of energy momentum conservation are implemented in quantum theory, dA, T, d mu, T mu is not zero, but it is equal to contact terms because, various fields are changing. And that's the structure you get. So in a sense, that is like getting the conservation of energy momentum tensor, right? Up to contact terms. And that just follows, as you were saying, from the boundary diffeomorphisms, which are constraint conditions. So maybe that's all we want. We don't want some special, U direction. We are allowing for big changes in the metric. We get conservation. I mean, that's what happens in the quantum analysis.
So these contact terms are physically the fact that the matter doesn't die off at it.
Yeah, it injects momentum energy or whatever others isolate.
Unlike in ADS, right? It doesn't raise the boundary.
Or if you put in non-normalizable boundaries, same thing would happen there. Yeah, right. Right.
Yeah, I mean, here at least for the talk that I presented here, the motivation is really to come up with the notion of Bondi mass loss formula.
You really want the energy.
Can I just make one? If I compare with what Brown and did, right. So there, the asymptotic conditions are not changed. I mean, there were no but there was a full phase space out of the normalizable modes themselves. Like the TAPs themselves had, the ln and l minus n themselves. So that is not.
So in ADS4 that doesn't happen. In ADS4, many people have tried such things. You always get SO3, 2 as the.
So the only thing is that BMS stuff.
No, even the BMS stuff you don't get. You only get SO. The ADS isometries is what you get.
So if you try to do, ADS isometries is all that you get because the consistency check that Brown and did, which is like a closure of the algebra of the asymptotic. That allows only this finite dimension.
That analysis. Also, of course, this is in some sense a game or an endless exercise. Like you first say this is what I want to allow. So let's say I want to allow for cut solution in ADS, and then I apply isometries of ADS. So I apply isometries of ADS on current solution, then I will get some set of boundary conditions. With those boundary conditions, I analyze what are the asymptotic symmetry groups. And that answer is just SO3, 2.
But my question was more like here for visitor. For visitor, suppose you say that you allow me these TABs. Would you have possibly, because it's a constraint system, so of course, even if the Boston bracket is non-trivial, the Dirac bracket trivial. The Dirac bracket.
So I think all the discussion is for the S3 compact slices. But if you consider non-compact slices, then I was saying there are multiple proposals in the literature. Which one to work with? And there is in fact a proposal lambda BMS, which is related to BMS.
Thank you.